Welcome to the Stat200 special lecture on the binomial distribution. It has an imposing sounding name, but it's really not that difficult. What it's used for? To compute the probability of getting a certain number of successes when I repeat an experiment or something over and over again, where the probability of success each time remains constant. As a simple example, if I flip a coin, a fair coin, 12 times, I might want to know what's the probability of getting exactly 8 heads out of 12 times. That's a simple example. A more important example might be in an election. Suppose that the actual reality is if I knew the whole population, that 52% of the population was going to vote for candidate X. Then I go and take a random sample of 16 voters, and I want to know the probability that I get it wrong. That is, that it looks to me from my sample that is less than 50% of my sample is going to vote for that candidate. That means what's the probability of getting less than 8 out of my 16 will vote for X, given that he's actually going to win because in the population there's 52% of the vote. These are the kind of things we're going to learn about. But we need a little bit of probability review for background. So first of all, remember that when I talk about the probability of A being some probability like 0.7, what I mean is that 70% of the population belongs in category A, or if I repeat the experiment over and over again, then 70% of the time I'll get somebody that belongs to group A. So when I say the probability of heads for a coin is 0.5, it means that if I run the experiment over and over again, in the long run, 50% of the time I'll get heads. Then when we study probability, we also study something called conditional probability, the probability of A given B, and we defined it to be the probability of A and B, that is the probability that they both occur together, divided by the probability of B. That's the computational formula, but what it really means is, this is, of all the B's, what part is A? Or if I restrict myself to the cases where B occurs, what fraction of the times will it also belong to A? And so I get that as, of all the B's, what part of B is also A? That's A and B. Now we bring up a new definition. We say that two events A and B are independent if the probability of A given B is exactly the same thing as the probability of A. Or in other words, the fraction of the whole population that's A is exactly the same as the fraction of the B's that belong to A. And we'll use this idea as we develop the binomial distribution. Okay, so remembering this definition, I'm going to erase this now, and then we'll look at what this means and do an example. So we have the probability of A and B divided by the probability of B. That's my definition of the probability of A given B. And if the two events are independent, then this is the same thing we just defined as the probability of A. Again, the fraction of the whole population that's A is the same as the fraction of B. This piece of the population that's B is A. But notice what happens if these two things are equal. I can multiply both sides by the probability of B. That's always a legal thing to do, multiply both sides by the same thing. If I do that, these cancel, and I get a new rule that in the case of independence, if this probability is the same as that one, then I get the probability of A and B is the same as the product of the two probabilities. This doesn't always work, it usually doesn't work. But in the case of independence, that's what I have. And so when I have independence, I can really think of it as a license to multiply. License to multiply probabilities. So, for example, I'll use the example right here. Suppose I flip a coin, and I want to know about the probability of getting heads, and tails. That is, the first coin is heads, and the second coin is heads, and the third coin is tails. If I assume that the results are independent, and that's a good assumption for coin flipping, then according to this rule, I can multiply the probabilities and say that this is the probability of heads times the probability of heads times the probability of tails. And if it's a fair coin, these are all 1/2. So that's 1/2 times 1/2 times 1/2, which is 1/8. So that would be the probability of getting exactly this result. Okay. So let's extend this a little bit and start looking at probabilities of a sequence of events, like the one we just considered. But first, let's just do one little counterexample. Suppose I have the following, that the probability of some event A is 0.7, again we'll use, and the probability of another event B is 0.6. That is, 70% of the population belongs in category A and 60% of the population belongs in category B. But the overlap, the probability of A and B, is 0.4. That is, only 40% of the population belongs in both categories simultaneously. And remember, we can draw this as a little diagram, Venn diagram. So here's my category A with 70%, my category B with 60%, and A and B is just that overlap. In this case, we said it was 40%. And by definition, the probability of A given B is equal to the overlap, 0.4, out of the second one, probability of B, 0.6, and that's the same as 2/3, or 0.6667. Now notice in this case, the probability of A and B, A given B, is different from the probability of A. 0.7 and 0.667 are different numbers, so in this case we don't have. So in this case, A is not, or A and B are not independent. Okay. So what we're going to do next is consider an unfair coin where we assume everything's independent. We have our license to multiply probabilities. So let's go there now. After this example of failure of independence, it turns out getting events to be independent is pretty hard. We have to have just the right conditions. Fortunately, coin flipping is one of them where we have that. So suppose I now have an unfair coin where the probability of heads is equal to 0.6. Well, I either get heads or tails, so that must mean that the probability of tails is 0.4. So now we can ask that same thing. What's the probability of getting heads on the first try, heads on the second try, and tails on the third try? Or if I have 3 of these coins, the probability of getting heads on the first coin, and heads on the second coin, and tails on the third coin. Again, if I assume independence, which I'm going to do for this whole exercise, then this means I just take the probability of heads times the probability of heads, because independence is a license to multiply probabilities. But now these aren't all the same. I have an unfair coin, so this is 0.6 times 0.6 times 0.4, or better known as 0.6 squared times 0.4. If I want to write that a little bit shorter. And if I use my calculator to calculate that, that's 0.6 times 0.6 times 0.4 is 0.144. Now that's not equal to an 8, which we had when the coin was fair. I've raised the probability, right? This is actually 1/8 is 0.125. So now I've got a higher probability of getting heads, heads, tails than I did in the fair coin case. And again, I'm using the fact that coin flips are independent, so I can simply multiply the probabilities. Okay, this is a good place to pause in our first section. Next, we'll consider the details of counting patterns.